Welcome to the first lecture of Math 646, which is a continuation of Math 645, Mathematical Problems 2. We will be teaching this class concurrently to local students, 7 students in the class, meeting Tuesdays and Thursdays, and also to 12 distant students. What I'd like you to do in the first lecture is just to go over some of the methods and goals for this particular class, particularly for the distant students. One thing I always encourage you to do is to check the news link, both on the table of contents side and on the main page. Clicking the news will give you the latest breaking events, latest first. Now, there are 2 versions of the course notes for this site. There's a student version of the course notes, which you are encouraged to print out and follow along and read. This is a 196-page document, or 148-page for the student version, by Professors Boas and Geller. There's also an instructor version, which contains some appendix information which you may or may not find useful. It's primarily for the purpose of the instructor. There is also a grader for this course, and he will be grading the mathematical problem sets. I will be grading the projects and any web contributions by the students. The class policy I want to go over at this point. This is Math 646, Section 600 for the local students and 700 for the out-of-state and distant students. Spring 2003. My name is Professor Michael Pylant. I'll be the instructor for this course. My web page is at www.math.tmu.edu/Michael.Pylant or just ~mpylant, as you can see in the web page up here. You can always reach me at mpylant@math.tamu.edu. My phone number has changed since I'm now an associate department head. The office phone number is 845-3261, and you can reach me physically for office hours in Blocker 623. Lecture times for this course are Tuesdays and Thursdays, 2:20 to 3:35 for the local students. I'll also have office hours on Thursdays in the lab from 3:35 to 4:40, and since most of the local students cannot make office hours at 1 to 2:20 for class conflicts, I will also have office hours in my office, Blocker 623, at the same time. So that is a change from the first day of class. You're also free to set up other times by appointment or email me to set up a time. There will also be some instructions on how to do virtual office hours for distant students, how to reach me on the weekends. The preferred is to leave either voicemail or email. The title of this course is called Mathematical Problems 2. The textbook, or the description in the catalog, is a survey of problems in various branches of mathematics, such as algebra, geometry, differential equations, real analysis, complex analysis, calculus of variations. The textbooks for this course are several. First of all, 646 course notes by Boas and Geller, which we've already seen before. I encourage you to copy this. There's 148 pages. The table of contents will go through, just a second here. We will be doing chapters 8 and following. So the first part was covered in 645. So we will not cover game theory, but starting with set theory and foundations, we will then go through limits, functions, plane geometry, extension of the real numbers, complex variables, and various projects, paradoxes, etc. There are also 645 course notes, which I commend to your reading by Professor Don Allen. He has quite a bit of information on here. He is also teaching Math 629, History of Mathematics this semester, and there will be some overlap in the early stages. The homework and exams and grading policy are not yet set in place, but I will give you some guidelines in a second in the overview. Makeup policy, scholastic dishonesty, and copyright policy, these are standard templates. The overview of the course is what I'd like to do next. Bring that up in a separate window. The course overview, as we know, mathematics originated in the far past, 3,000 or 4,000 BC, as our ancestors tried to understand the world around them. So first of all, we're going to begin with a small historical segue and survey some of the role that problems and problem solving has played in the historical development of mathematics. So in Lecture 1, we're going to cover Mesopotamian and Egyptian mathematics, and there's an appropriate section in Math 629 that we'll find here. This will be covered in Lecture 2. After we have 1 or 2 lectures on the historical origins of problems and problem solving, which evolves into proofs and rigorous techniques for mathematical thought, we will go over the basic elements of problem solving. First of all, the process of modeling, or going from a physical situation such as surveying or calculating the area of a field or an irregularly shaped field, to develop a model. We'll go into the idea of abstraction, how to convert that to a symbolic statement, a mathematical statement. We'll talk about the general role of conjectures in forming mathematically correct statements, the role of hypotheses, and the role of proofs, both heuristic and rigorous proofs. And finally, the bread and butter of contemporary mathematics, the role of generalization and the development of new mathematical areas. So we'll be covering the material from chapters 8 through 13 of the manuscript of Boas and Geller. And then in the last part of the course, we will focus on historically significant problems as well as current or fundamental problems in the following areas: algebra, algorithms and complexity, calculus of variations, complex analysis, differential equations, proofs, logics, foundations, paradoxes, and finally real analysis. So the idea is that students will select 2 or 3 of these topics in consultation with myself as the instructor, and then you as a student will first identify several historically important problems that gave rise or affected the development of these mathematical area. You will then construct a web page summarizing your research. If you have difficulty constructing such a web page, I can help you, or you can just email me a Word or PDF document and I will archive it under a directory in your name. There will be 2 or 3 fundamental problems I'll give you, more or less customized for you as an individual, separate and different from other students. The solution of these will then be graded by myself or the grader. Then the students will have an option to either take a take-home final or do a final project. I've assembled a number of readings for this course, which are also of interest from both a historical point of view and otherwise. So let's look and see the new, or the version of readings as it currently is. I will be adding to these over the course of the semester. So first of all, the first example of a link that pertains to this course is famous problems in the history of mathematics. I'll let you go through and read this. I won't read it to you. However, I point out that there are several historically important problems here. First of all, a great problem called the Bridges of Königsberg, which inspired Euler to invent a whole new theory of mathematics called graph theory, and which in turn led into the development of topology. There is a nice link on the history of the value of pi, how mathematicians through the centuries have increased the accuracy of their approximations to pi from 3 to several billion decimal places right now. Prime numbers, famous paradoxes such as Zeno's paradox or Cantor's infinities, the problem of points, probabilities, card playing and gambling actually gave rise to a theory of probability by Pascal. Proof of the Pythagorean theorem. This is one of the oldest proofs in mathematics, coming from Greek days. A more contemporary problem, proof that E is irrational. And there are other links here that you're free to look through. A very famous source of historically important problems are the so-called Hilbert problems. I have several links to that. Here is an enumeration of the problems along with some historical background. Each of these is a problem number, a statement, and the current result. So some of these were solved in the affirmative, or some of these were actually given negatively or a counter example. Some of these are fairly new. One of the very famous historical theorems is Fermat's theorem, which has just been recently solved. Here's another link to Hilbert's problems. There's an actual link to the address that Hilbert gave at the International Congress of Mathematics in 1900, the Centennial Address. Here is a very interesting source. This is an interactive book, Euclid's Elements. And you can actually go down, select a book, say Book 1, and there will be links to applets, definitions, etc. So each of these has an applet that you can actually play with here. So these are very nice little applets, interactively generated here. So I commend this to your reading. There is also a link to the International Math Olympiad problems, which are a very famous source of problems that are periodically given. There's a link to some math books of general interest, as well as an archive of Putnam exam problems, which are United States William Lowell Putnam exam. And a very nice site containing over 3,600 Olympiad problems, 900 Putnam problems, complete with solutions. So if you click on the link to the Putnam exam, this site contains 807 problems, complete with solutions, up except for a few years. Now the way these work is you can go to a PDF file that contains just the problem statements, or you can click on a Putnam link, and it will contain the statement of the problem, and for those links that contain an icon, which should be here but hasn't shown up yet, if you click on the icon, it will then take you on a link to the solution problem. So here's the solution of problem A1. A and B are positive reals, A larger than B. Let C be the plane curve R equals A minus B cosine theta, for what values of B over A is A C convex. And this contains a detailed solution. Here's the solution icon right here. So on any of the particular problems, does the series summation 2 to infinity 1 over log n and factorial converge? Does the series, etc., converge? So you can find the solution of these. This is quite a nice archive of interesting problems. There was also a very nice article on teaching with original sources. One of the approaches that one can take when teaching mathematics is to do it from a historical perspective, or actually go through as if you were discovering new mathematics without any background, reading the original sources for the very first time, how mathematicians view problems. Now there is some actual benefit to going back to the original historical sources, because later editing often compresses the solutions so much as to almost be not understandable. This particular site has a nice article in the AMS journal, and you can get this in a PDF file. So this is an article appeared that in the American Mathematical Monthly in 1992, and the PDF file is here. So this is a PDF file that appeared here. So I also commend that to your reading. This takes you on a very quick survey of this course. The table of contents will be expanding. If you click on the lectures, the first lecture will be on Mesopotamian and Egyptian mathematics. That will actually be the first formal lecture. This is essentially the introductory and background of the course policy. I also commend, again, that Professor Allen is teaching Math 629, which is history of mathematics, and he has a number of very nice links, some of which, as in this chapter, cover Egyptian and Babylonian mathematics, which will be the subject of Mathematics Lecture 1. Please feel free to email me, the instructor, mpilon@math.tmu.edu. Contact me, my phone number, and read and or download the lectures as they are available on the web. There will be a link on the left column, which will appear shortly, which will give you a way to review the lectures and also download the lectures. At the end of the course, a CD will be made containing the website as well.